तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, in the last class we started discussing about a wideband amplifier, which is a cascade structure. A cascade you get when you cascade common emitter amplifier to common base amplifier or common source in the FET case to cascade it to common gate. What is the virtue of this? How did we get the widebanding? Widebanding is always got in all these cascaded structures by maintaining the time constants low. Wherever time constants occur, we try to maintain these low. How do the time constants occur? The real part of the impedance and capacitance. These cause time constants at their respective terminals. So, this in a cascade structure, this is the input time constant caused by input resistance, source resistance and input capacitance. Intermediate time constant is caused by output resistance, input resistance parallel and then capacitance at this junction. And this time constant is caused by the load, the output capacitor and the output resistance of the structure. So, obviously capacitors have to be minimized, and we saw how cascade structure reduces the input capacitor of the so called common emitter amplifier, and that way it retains the low frequency characteristic of the common emitter amplifier, but can be used for wide band of frequencies. So, let us put down the equivalent circuit. Now, as far as high frequency equivalent circuits are concerned, for the bipolar, you start with, in the case of common emitter high frequency equivalent circuit, you start with base. So, this is B, and then you have a physical resistance called RBB prime. This is the base resistance from the junction to the contact. This should be made as small as possible. This is of the order of few ohms, tens of ohms. And then we have the actual junction coming into picture, that is called B dash, because from the actual junction up to the base contact there is an ohmic resistance. Then junction comes into picture, and once we have the junction, we know that there is a resistance RB dash E, which is actually speaking, RB dash E is actually equal to your RE, which we have been calling as RE, Vt over IE into beta plus 1. This is the normal impedance which we have been using for common emitter amplifier, except that there is some ohmic resistance of the order of tens of ohms added to that. Since this is of the order of kilo ohms, in normal practice this is always ignored. But at high frequencies, you will see there is a visible change in the characteristic, because the capacitance Cb dash E, the junction capacitance, comes directly across the junction. So, this is Cb dash E. So, we have the emitter here. Then from the base to the collector, there is a capacitance, because it is a reverse bias junction. So, this is Cb dash C. This is going to be lower in order of magnitude, because this is a forward bias junction, right. This capacitance is called diffusion capacitance. Okay. This is going to be pretty high compared to Cb dash C. So, this Cb dash C is the capacitance, reverse bias junction capacitance. This is called transition capacitance. This is the depletion layer capacitance. It depends upon the reverse bias voltage. As the reverse bias voltage across the junction increases, this capacitance decreases. Then we have our usual low frequency structure, which is Gm into Vb dash E. This we have been earlier calling just Gm into Vbe. This current source which we have earlier used, Gm into Vb dash E. So, then actually Gm is alpha divided by Re according to us, the low frequency. That is going to give you the low frequency collector current, and across the collector we have the so called RCE. That current source is not ideal current source. There is a shunt resistance RCE, typically of the order of few mega ohms in the case of integrated circuit transistors. So, this is what is called hybrid pi equivalent circuit for BJT. Hybrid because this arm and this arm form a pi, but there is a T added to this, L added to this. So, it is called hybrid pi equivalent circuit, which is the most commonly used equivalent circuit for a common emitter transistor at high frequencies. In fact, you can put a high resistance across this, which that this resistance is going to be of the order of hundreds of mega ohms. So, that is of no consequence for high frequencies. So, these are the important part of the equivalent circuit. So, when we discuss a wideband amplifier, we should put down this equivalent circuit in order to do the analysis. In the case of field effect transistor, the same equivalent circuit is very simple, because it starts with gate, and gate obviously is insulated from the source and the drain. So, there is only a capacitance actually from gate, this is the collector terminal. So, gate to the drain, okay, there is only a capacitance which is called CGD, where the gate overlaps slightly the drain. If it does not overlap, this is 0, but it is very difficult to make it not overlap, right. So, this CGD is going to be very small, but it is there. Then similarly, we have similar to this capacitance CGS is going to the source. So, these capacitances are there. These are occurring here because of the junction. Here these capacitances occur because of the overlap between gate and drain, gate and source. With ion implantation technique etc., this overlap has been made very nearly 0, and therefore, these capacitances can be made very low. Then we have the same thing GM into, in this case, VGS, the low frequency equivalent circuit that we had discussed earlier. So, exactly same as that, and then across that we have RDS. In most of the cases, this is the high frequency equivalent circuit of the FET, okay, JFET or MOSFET. It is the same equivalent circuit. Only difference is, if these are discrete circuit, this is the equivalent circuit. If they are integrated circuit components, then these components lie inside what is called a well. A substrate has large number of wells where these devices are put, and that each of these well is separated from the substrate by a junction which is reverse biased all the time. So, that is how you separate one device from the other, and therefore, there is what is called as substrate capacitance in each of these cases from this collector well, okay, or this well, we have a substrate capacitance. So, normally this capacitance is there both from the drain as well as the source here, but fortunately source is connected to substrate in most of the cases. So, this capacitance is not going to be of consequence. So, in the case of common source and common emitter amplifiers, this is going to be the equivalent circuit. That means, this capacitance is going to be part of the output capacitance. So, we should have a complete picture of the equivalent circuit of the active device in order to understand and appreciate the limitations in bandwidth. Now, let us take the case of cascode and put this hybrid pi equivalent circuit and see what the time constants will be. So, in a normal common emitter transistor, this collector is connected to a resistance RC. So, in a sense, we have RS this is for the common emitter high frequency equivalent circuit. So, if you forget these capacitors, let us look at only the low frequency equivalent. RB dash E comes in series with RB B dash. So, it is essentially RB dash E itself, okay, totally, and that comes in series with RS. So, the gain gets reduced here to a certain extent by RB dash E divided by RB dash E plus RS plus RBB dash. So, when the voltage comes here, Vs into RB dash E divided by RB dash E plus RBB dash plus RS is nothing but VB dash E. The VB dash E voltage here, okay, at low frequencies. This into GM is the current in this Gm into Vb dash E. That current will flow into the parallel combination of RCE and RC. So, this into RCE RC divided by RC plus RCE. Okay. That is with a negative sign, because V naught we are going to define as this. So, this is going to be V naught, because current is flowing like this, it will develop plus minus as the polarity. So, you see that this is the low frequency gain. What is it? Gm RC. Actually, if it is RC is very high, let us say compared to RC, it will be Gm RC. Okay. And here it is RB dash E divided by RB dash E plus RBB dash plus RS. If this is very small, this again is going to be very nearly equal to 1, and essentially the gain is going to be minus Gm into RC. Okay. That is if RS plus RBB dash is much less than RB dash E, which is the case most of the time when you are using a voltage source drive. Okay. The gain of the amplifier and then RCE is much greater than RC. This is the normal gain of a common emitter amplifier. Now, what happens at high frequencies? So, I would like to obtain V naught over Vs at high frequencies. So, we will call this as our A naught, that is the gain at low frequency, DC indicating A naught. Okay. So, at high frequencies V naught over Vs becomes minus A naught divided by, let us see, 1 plus S by omega P1, 1 plus S by omega P2. Approximately. This we discussed in the last class, how it becomes. Let us see. The approximation is Cb dash E is this capacitance, and this Cb dash C gets amplified because this is the input and there is a gain of Gm into RC parallel RCE, that is the low frequency gain. So, it gets amplified by this Cb dash G gets amplified by that factor 1 plus Gm into RC parallel RCE. So, I can convert this capacitance, this is the approximation, even though at that point I am not considering the frequency dependence of the gain, but it is going to give me more capacitance than what is actually going to exist, because the gain is going to reduce anyway, right. So, I am actually overestimating the actual input capacitance. So, I am safe. So, this is going to simplify, this is going to be Cb dash C into 1 plus, this is the Miller effect which we discussed, Rb dash, there is RCE parallel RC. So, RC parallel RC is very nearly equal to RC itself, that we had earlier mentioned, and across this now we have a capacitance of CB dash C coming into picture. The Miller effect is at the input it will be CB dash C into 1 plus GM RCE parallel RC, and at the output it is CB dash C itself very nearly. So, now we can indicate what omega P1 is going to be. Omega P1 is going to be the time constant at the input. It is determined by the time constant at the input. It is 1 over the time constant. So, 1 over what is the net resistance across these capacitors, RB dash E RB dash E parallel RBB dash plus RS. This is important. If it is driven by a current source, RS is infinity, then this will be just RB dash E. If it is driven by an voltage source, it will be very nearly 0. That means this time constant does not come into picture at all if it is a voltage source here. Normally, even if RS is 0, RBB dash comes into picture. That is why the significance of RBB dash at high frequency. Even if you are able to make RS equal to 0, there is a series resistance which is RBB dash. So, essentially it will be RB dash E parallel RBB dash plus RS into CB dash E plus CB dash C into 1 plus GM RC parallel. So, that is omega P1. That can be written by observation. Always find out the net capacitance and the net resistance across the capacitance. That will determine the time constant at any point. Okay. So, CB dash E plus CB dash C into 1 plus GMRC parallel RC is the net capacitance. Across that capacitance we have a resistance of RB dash E parallel RBB dash plus RS. So, as far as omega P2 is concerned, this is going to be 1 over the time constant at the output. Let us see. Effective resistance is simply RC parallel RCE. Effective resistance RC parallel RCE, and effective capacitance is C B dash C plus C substrate, or which is also called C stray, okay, any stray capacitance that comes. So, you can see that this capacitance is very small compared to this capacitance, which depends upon the gain of the structure, which is likely to be high, and therefore, this time constant normally dominates, and that is the bandwidth. How to improve the bandwidth then? Then that is why we had gone for a cascode structure. What happens in a cascode? All these things remain the same, only thing is now there is no RC here. Instead of this RC, we have here just about RE. That is a common base structure. Okay. The resistance here is RE very nearly. So, it is almost a short circuit at that point, and if this is the current I, then the current here is going to be, that is the equivalent for the common base. At this frequency at which this is functioning normally, common emitter, this common base normally need not be replaced by hybrid pi equivalent circuit. Even if you replace, you will note that ultimately the effect is only due to that, this common base structure, which is I and alpha times I, and alpha cutoff frequency of this BJT is beta times the beta cutoff. Okay. So, if common emitter is having a current gain which is beta, its cutoff frequency let us say is 100 megahertz, then if the beta of the transistor is 200, okay, this will be 200 times 100 megahertz. Since we are going to use the common emitter only in the range of 100 megahertz, there is no point in replacing this by its common emitter equivalent circuit and then finding out what the common base equivalent is. You can as well replace it by the common base equivalent, which can be the low frequency equivalent. So, alpha times I and then R C, and this resistance of course is beta plus 1 times R C. This is for the common base, the output impedance is beta plus 1 times, okay, the common emitter output impedance. Okay. So, this resistance is going to be of the order of hundreds of mega ohms. Anyway, that is what we had ignored in the equivalent circuit earlier also. It will come across C B dash C, right. So, that resistance is normally ignored. So, this is the equivalent circuit, that is R C, that is all. So, what this does is this does not take part in deteriorating the high frequency performance of the structure, but this part of the thing as far as the common emitter is concerned, its high frequency performance is improved, because Miller effect is now just this is Gm, and if both are operating at the same current, this will be 1 over Gm, and that this is going to be 1 plus 1. Okay. And by the same token, this Cb dash C will be 1 plus 1, that is 2, that is an increase here, right, because that the gain is now not negligible. So, the output voltage and input voltage, they are of the same magnitude, but opposite in phase, right. So, we get 2 Cb dash C here at the output and 2 Cb dash C at the input. Is this clear? So, 2 Cb dash C, 2 Cb dash C there, and therefore, this simply becomes so that is the thing. And as far as omega P2 is concerned now, the resistive part is no longer RC parallel RC, it is RE parallel RC, okay, which is RE itself very nearly. So, you can see, because not only this capacitance is low, now this particular resistance part is very low. Therefore, this frequency is shifted to very high frequency end. So, this goes very high, this is the intermediate pole. So, this is very high, this is still perhaps dominant, because this resistance is not very small, this capacitance is quite small, but compared to this it is still large, right, but it has been reduced from the earlier value, and ultimately now it has a third pole. As far as the low frequency gain is concerned, it still remains A naught, because this current and this current are one and the same, and it is still flowing through RC. So, the low frequency gain still remains Gm into RC. In fact, it is just now Gm into RC, no RC parallel RC also comes into picture. So, it is simply Gm into RC. So, omega P3 is the time constant here. Here we have a capacitance of course, which is nothing but C B dash C, the same reverse bias capacitance, okay, and maybe this C substrate. So, we have 1 by okay, RC into C B dash C plus C substrate. So, you have 3 time constants coming into picture in determining the gain of the structure. So, what will be the gain? Therefore, for the Cascode structure, I can write down the gain as V naught over V s as R b dash E divided by R b dash E plus R b b dash plus R s, that attenuation is always there, okay, into G m into R c with a negative sign, G m into R c with a negative sign, then divided by 1 plus s by omega p 1, 1 plus s by omega p 2, 1 plus s by omega p 3. So, this is the gain of the Cascode structure. Once again you see that it is very nearly same as the common emitter gain, except that now the time constants here have become lower than that of the common emitter. So, the bandwidth becomes higher. So, either this or this is normally very high. So, this does not come into picture in most of the cases, you can see, because this is R e, right. So, almost nearly short circuit. So, this pole is of no consequence at all, right, and it is really speaking a 2-pole system even now, because this pole, intermediate pole, is at very high frequency, at which point the gain might have fallen off to less than 1. So, this because of omega p 1 and omega p 3, the gain fall off occurs, right. Which one is the one that is going to determine the cutoff frequency really now depends upon the magnitude of the source impedance as well as the magnitude of collector resistance. Normally, right, the if it is a voltage drive, okay, the source impedance may be very small, in which case it is this that fixes up the bandwidth. Now, you can see that this is very good, because this is going to result in very large bandwidth for your structure. Take typically R c is, let us say, 1 kilo ohm, if you have R c of 1 kilo ohm and G m, let us say, is 40 millisiemens, G m into R c is going to be 40, gain of 40. So, now omega p 3 is going to be R c, that is 1 kilo ohm, okay, into let us take the C b dash c typical value, right. With the integrated circuits, these will go to fractions of picofarads. Maybe with individual distinct circuits, we can take typical value of 1 picofarad, let us say. If it is 1 picofarad, right. So, we get omega p 3, which is 10 to power 9, okay, radians per second, kilo mega radians per second, or in terms of this thing f p 3 is equal to 1000 by 2 pi, okay, megahertz. Which is a very high frequency. So, even if you consider this as few picofarads, this is going to be definitely usable for wideband amplifier, that is video amplifier, which is of the order of few megahertz. So, this kind of structure is pretty common. So, now that we have to use this hybrid pi equivalent circuit quite often in understanding video amplifiers, let us see how some of the low frequency parameters which we know of are related to the high frequency equivalent. This is the common emitter transistor, this is the hybrid pi equivalent. So, at low frequencies these capacitors are not coming into picture. So, I know that I short circuit this, then IC by IB is called beta by definition. It is called short circuit current gain of a common emitter transistor. That means this is shorted. This is what you are going to do here, short the output. And short circuit current gain is defined as beta. At low frequency it is beta naught, independent of frequency. At high frequency we would like to know what it is. So, the definition remains the same. At low frequency this is called beta naught. So, at high frequency we will call that as beta and see what that beta is going to be from this. So, let us see here. We have RBB dash and RB dash E. So, when I apply a base current IB into this and output is shorted, okay, this VB dash E at low frequencies or this VB dash E is going to be essentially equal to IB is independent of RB dash, because now I am putting IB as this current. So, RBB dash does not come into picture, this IB will now flow through, this is shorted. So, CB dash E comes in parallel with CB dash C. So, effectively you have a resistance RB dash E. So, IB dash E into RB dash E divided by 1 plus SC B dash E plus CB dash C into RB dash E. So, this is VB dash E. This resistance comes in parallel with the combination CB dash E plus CB dash C. So, that is IB into RB dash E divided by 1 plus S CB dash E plus CB dash C to RB dash E. This is what VB dash E is. That into GM is the current in this, and that is the short circuit current. So, this is the short circuit current IC, short circuit current. So, IC by IB from this is nothing but, we will call this beta equals RB dash E. Let us see, RB dash E GM divided by 1 plus S RB dash E into CB dash E plus CB dash C. Now, what is RB dash E? We will expand that. This is also equal to RE into beta plus 1, that is RB dash E. And what is GM? Alpha by RE. So, alpha by RE. And what is alpha? Beta alpha is beta alpha naught, let us say alpha naught, beta naught divided by beta naught plus 1. So, alpha naught. So, alpha naught is beta naught, okay, So, you can see here this is low frequency wise nothing but beta naught itself. This whole thing in the numerator is nothing but beta naught. So, we can just say that this is equal to beta naught divided by 1 plus S into, now R B dash E is R E, okay, into beta plus 1. So, we will put that C B dash E plus C B dash C into beta plus 1, beta naught plus 1. So, you will see that beta at low frequency falls off at 20 decibels per decade. This can be written therefore as, this is going to be beta naught by 1 plus S divided by omega beta. Omega beta is called the cutoff frequency. Omega beta in this case is nothing but 1 over R E into C B dash E plus C B dash C into beta naught plus 1. This is called the beta cutoff frequency. So, this is determined by R E into C B dash E plus C B dash C product, okay, that into beta naught plus 1. Let us now see what is alpha. Alpha at high frequency is nothing but beta at high frequency divided by beta plus 1. This we always know. Okay. So, this is equal to, let us write it as let us say 1 by 1 plus 1 over beta. Okay. 1 over beta here can be substituted from this as 1 plus S by omega beta divided by beta naught. Okay. So, we will rewrite this as beta naught divided by beta naught plus 1 plus S by omega beta into beta naught. One plus 1 by beta naught, that is this beta naught comes here, beta naught sorry, this is just this beta naught here, beta naught comes to the numerator. So, beta naught by beta naught plus 1 plus S by omega beta. So, I will take out beta naught plus 1. So, this is equal to beta naught divided by beta naught plus 1 divided by 1 plus S by omega beta to beta naught plus 1. What is beta naught by beta naught plus 1? Alpha naught. So, this is nothing but alpha naught. So, alpha is going to be alpha naught by 1 plus S by omega beta to beta naught plus 1. So, alpha cutoff frequency, this is beta cutoff frequency. So, alpha cutoff frequency is equal to omega alpha, we will call this as omega alpha, equal to omega beta into beta naught plus 1 from this. And we also know omega beta. Omega beta into beta naught plus 1 is nothing but 1 over R E into C B dash E plus C B dash C. It is an important parameter, okay, alpha cutoff frequency. Beyond this, there is no worthwhile gain, current gain for the transistor at all, right. So, this is also called FT, the transition frequency, or it is that frequency, it is f t is very nearly equal to, sorry, omega t we will call this dimensionally omega t instead of f t is omega t divided by 2 pi. So, this is called transition frequency. What is transit? The gain actually after this frequency becomes less than 1, that is beta. If you consider beta itself is going to fall to a magnitude which is less than 1, okay. And or alpha becomes 0.707 times alpha naught. So, it is the upper cutoff frequency of alpha, or where beta falls to less than 1, that is the transition frequency, and this is parameter which is given by the manufacturer. That is why, so omega t if it is given, Re can be evaluated depending upon the operating current. Re is equal to V t divided by I e q. Then you can find out what is C b dash E plus C b dash C. Okay. So, the effective value of this capacitance can also be found out if omega t is given. Manufacturer normally gives omega t, okay, and therefore, you can find out the value of C b dash E plus C b dash C from that. So, this transition frequency f t is one of the important parameters, high frequency parameters, which is absolutely necessary to design any high frequency circuit. This is really speaking, okay, 1 over Re is Gm, okay. Normal gain is Gm into Rc, and the bandwidth is Rc into some capacitor C b dash E plus C b dash C. So, gain bandwidth product, it is a measure which is called gain into bandwidth product, okay. Current gain into current bandwidth, okay, gain bandwidth product it is also called. This is the same thing, even in the case of a FET it is Gm of the FET divided by C total, okay. So, this is C, instead of C b dash E plus C b dash C, there we will use C g S plus C g D. So, this parameter is quite often used in evaluating the performance of high frequency performance of all the wideband amplifiers.